Hey guys, Matt here again for our third video in the three-part series, and today we're going to go over how to use the computer-aided manufacturing side of Fusion 360. So go ahead and pull up the ViceJaw demo that we did in video number 2, because that's what we're going to be using for this series. Now, over on the upper left-hand side, you have a bunch of different modules within Fusion 360. Design, generative design, render, which if you're creating realistic renderings for product design, animation, where you can animate your parts to make them actually work. Simulation is like heat and thermal, finite element analysis. Manufacturing, which is the CAM side, and then drawing. We want to be in the manufacturing workspace. So hit manufacturing. The first thing that we need to do whenever we go into the computer-aided manufacturing side is to create a setup. So in the left-hand corner, we're going to create new setup. Okay. The first thing is, well, we're not necessarily machining this quite yet. We're machining these. Okay, so that's going to be our model. On our stock, well, actually, before I move from that, it's asking our work coordinate system's orientation. So on orientation, I always choose select Z-axis and X-axis. So I choose my Z-axis, and then I choose my X-axis. And now, if I were to look down at my vise, that's exactly how my vise would be. This would be the movable jaw. This would be the fixed jaw. Okay. Now I can choose my stock point, or I can choose my model point. In this case, I'm going to choose model. And I'm going to choose, you know what? I'm going to choose selected point, and I'm going to choose that corner, right? Because that's my fixed jaw, and that's the interior face of my fixed jaw. So I like that. On stock, I'm going to choose relative size box, but I'm not going to add any stock to that because I designed it with no stock allowance. And then on post-processing, this is a little bit confusing for some people, but it doesn't need to be. Instead of saying 54, 55, 56, 57 for your work offsets, it's 1, 2, 3 all the way through, 99. So in this case, work coordinate system 1 is G54. Number 2 is G55, and so on and so forth. If you're working on a machine like the Akuma, it actually just uses 1 through whatever. It'd be G15, H1. In this case, I'm going to use work coordinate system number 1. Okay, so that's where out on my machine I need to stick my G54. Okay, so I've got my setup complete. I'm actually going to come here and I'm going to hide my stock for a minute. The first thing that I always start with is a roughing strategy. In this case, my vice jaws are all the way to size except for my cutouts, right? Because I'm using aluminum vice jaws to hold a cylindrical part. So the first thing I need to do is a roughing strategy. 2D adaptive clearing is the safest roughing strategy in my opinion, because what it doesn't allow you to do is bury the tool in the corners. Imagine if you've got a sharp 90-degree corner internal. The tool, and this is just so you can visualize a little bit, if we're cutting on the inside of this, it's going because now you've got 180 degrees of the tool now in contact, whereas it used to only be a smaller fraction of it. What the 2D adaptive clearing toolpath will do is it won't bury the corners. It will carve out the corners using little D-shaped toolpaths. So I'm going to go ahead and use that. It brings up this dialog box here, And this is common to every tool path that you're going to be using in Fusion 360. It first asks me to select a tool. Well, I can save tool libraries if I want. In this case, I haven't for that part file. So I'm going to come all the way over here to Cutter. I want to use a flat end mill. It's a 3-fluter. It's made from carbide. I need to go back and change my units to inches, but it's going to be a 3/8 size diameter tool, so 375 thou. Go ahead and change all these things if you need to. On my feeds and speeds, okay, so this is very easy. This is where you don't need to get all crazy on calculating speeds and feeds, because Fusion is going to do it for you. On my surface speed, if you have your speeds and feeds chart that we give you in this class, you know that you can go up to at least 1,000 surface feet per minute in aluminum. Well, this is saying that it'd be 10,185 RPM. Sounds good to me. On my feed per tooth, again, if you flip that sheet over, it will tell you that you can go up to, 4, 5, 6 thousandths chip load per tooth. So that's going to generate a cutting feed rate of 152 inches a minute. Now, do I need to go that fast? No, not necessarily in this class. You certainly don't need to. And on the Haas, you won't be able to. So if I decrease my surface feet or my spindle RPM on the Haas, you're limited to 7,500 RPM. That's going to dynamically change your cutting feed rates. If you want to ramp into, so if you're doing a helical interpolation, typically your ramp spindle speed changes. And I like to go 30% below. In this case, I'll go 5,000, and that's fine. And then if I right click on ramp feed rate and hit reset to default, let's see. Yeah, it'll change that. Notice that these feed rates are different than the lead in and lead out feed rate. Coming over to post processor, this is your tool number. So if you made it tool number 5 on the Haas or Yakuma or anything else, you would stick number 5 in there. If you want flood coolant, great. If you don't want anything, you can disable it. If you want air, like on the Yakuma, you can do that. And hit OK. Hit OK. So now you can see that those spindles, feeds and speeds are now populated into this. And it's all metric, which is driving me crazy. So let me change that real quick. Before I do that, I need to select my geometry. And in this case, it's going to be those 2 pockets. Notice I didn't need to select a vertice or anything like that. I can just select my actual pocket floor. And when I go to heights, really the only one you want to worry about is the bottom height. And that's just the selected contour that I did. Now, if you want to offset it up or down, you can do that. And that's where you would do it in the offset. So now I'm going to hit OK. And that's going to generate a tool path. Before I forget, I want to change my units from millimeters to inches. So I come over here, units, hit the change active units, move that to inch, and hit OK. Now, thankfully, everything is in American. Okay, so now my speeds and feeds look correct. Now I want to come over to this third tab, and this is the passes tab. This is where I can set an optimal load. Now, I don't ever like to work off of, a set inch amount. I like to work off percentage of the tool's diameter. And typically for these tool paths, they work best between 5% and 40% of the tool's diameter. So for round numbers, let's go 10%. 10% of 375 would be 0.0375. So it's going to take 37 thousandths per pass. I'm totally good with that. If I want to leave some stock, I can do that. In this case, 20 thou is a little bit too much. I'm going to leave 5 thou on both the top and the bottom for a finishing path. And I can see it's making little D-shaped tricoidal tool paths. Looks really good. If I want to simulate that, I right-click on the tool path and hit simulate. I want my stock to be shown. I don't care about having my tool path shown. Now, because of the way I did this, there's all this stock in the middle. Obviously, there's not going to be that stock in the middle because, it's just not. These are your two vice jaws. So don't worry about it plunging into this stock. As long as it's moving from the outside, you're good, which it is. You can see it taking off, that 37.5 thou. Looks good. Looks good. Now, if you were to scroll along here and you see anything that's red, that is a crash. Now, if I were to hover over it, it says rapid collision with stock. So what was happening is the tool was coming down in a rapid move into the stock. But again, there won't be any stock there, so we can go ahead and disregard those. If I come over to the Info tab, you can see that the total time to machine that should be about 53 seconds. Again, you can come over to statistics, a little bit easier. It tells you the amount of operations, the tool changes, etc. Okay, that looks good. Now, in all of your roughing tool paths, you're not going to have cutter comp on, okay? Because anytime you make a z-axis move, the machine has to cancel cutter comp. So you just don't want it on roughing tool paths. That's why we leave a stock allowance. In this case, I left 5 thou on the walls and 5 thou on the floor because I want to clean that up later. So I'm going to come to 2D and I'm going to come to 2D contour. I'm going to use that same tool, might as well. And in picking my geometry, I'm going to pick these two contours. And you can see this red arrow. This is the side that the tool is going to be on. So if I were to click it, it would be on the other side, which would be the wrong side in this case. My height, my bottom height is still that selected contour. My passes, I do want multiple finishing passes on there. And on my step over, I'm going to say that, yeah, okay, maybe 15 thou is okay. And I'm going to have probably 5 passes to account for that. Now, my finishing feed rate, I could change here, but I'm also I like changing it here. The only thing I need to change is my feed per tooth. And going from 5 thou per tooth, I'm going to change that down to 1 thou per tooth. And you can see how all these changes after I put reset to built-in default. Okay, so now it went from 120 something inches a minute down to 22 inches a minute. So we're going to have a slower feed rate, which is going to make my hills and valleys on the walls of my part less extreme. Over in this passes tab, under compensation type, I'm going to choose wear. That's going to put a wear offset into my program. So I hit compensation type wear, thou output G41, and then I'm going to hit OK. And you can see that now we've got our roughing toolpath as well as our finishing toolpath on the wall. We've got a toolpath that looks okay, right? And when we simulate that, I'm concerned that it's not going to cut this portion very well. So instead of simulating it from this contour, I'm going to choose the setup to simulate. And then all I need to do is come down and click contour. And it will do everything above it just like that, which is a very, very cool feature. So very time-saving feature. So scale this back, run a little slow, let's see what I'm working with. See how we're just barely missing that? So I'm going to go ahead and change that a little bit. It doesn't need to be over my passes. My step over for my finishing doesn't need to be that light. I mean, I could do 3 passes of 125 thou, and that would work. Yep, so now I'm covering everything. So that looks really good. I'm just going to verify it. I can speed that up if I want. Now you can see there's a break in between operations. So if you ever just want to go to it, it will change between green and gray depending on which one you're on. And if you hover over it, it will give you the details of that operation. Okay, that looks great. Okay, so that's a good toolpath. I'm happy with that. Now I can go ahead and post-process that out to my machine, and the way I do that is I just right-click on Setup, or just the operation that I want to post-process. In this case, I want it to be both, so I right-click and hit Post-Process. Now I can choose generic posts, and I can come down to pause. And for our machines, it's just going to be a pause, just this pre-NGC pause, easy. And then my program number, date of birth for me. You can do whatever you want. And then I can hit OK. I can choose where to save this. I'll just save it on the desktop for now. And now, this might be a little hard for you to see, but now I've got my program that posted out. And so this will help you when reading your G codes. Okay, I've got tool 5 doing a tool change, the RPM 7500 and G54. Just by utilizing that information right there, you can see that things are right or they're wrong. If this was saying that it was only 750 RPM, you know that you fat fingered something, and you'd go back in your program and fix it. Okay. Now you would take that over to the machine, plug in the machine, do your work offset on this corner. Okay. If I ever want to see where it's at, I just hit the setup button. And if I ever want to know what it is, I just hit edit over to post process, and that's work coordinate system 1. Again, 1 is 54, 2 55, 3 56, so on and so forth. So that's a very simple part. We went over roughing and we went over a contour toolpath. Okay. What if we wanted to add some, I don't know, holes or something like that? What if we wanted to drill? We're going to go over to this this guy that we did earlier, and again, when I come into my manufacturer workspace, I need to hit setup, and I need to create a new setup. In this case, let's say that I've got some stock that's just oversized. Let me change the units real quick. So we are Americans. Go to setup, new setup. I'm going to change my z-axis. So orientation, I select z-axis and x-axis. That's my z-axis. We'll make this my x-axis. And that's fine. I can make this the center of my part. Okay. Over on relative size box, I'm just going to add, maybe it's 100 thou per side. And maybe we've got 100 thou on the top too. That works. I'm going to make this work coordinate system 2 or G55. And I'm going to hit OK. So it's in the center of my part and it's on the top of my stock. Let's go ahead and face this off since we've got that 100 thou that we're going to work with. So I'm going to hit face. I'm going to create a face mill. Let's call it a 5 fluter. This is carbide. The diameter is a 3-inch tool. Go over my speeds and feeds. That's a little, it'll work for aluminum, but in this case, I'm going to go with something a little bit more conservative. I'm going to go with a 4 thou chip load per tooth. Everything looks good, and I'll say that's tool number 6. Hit OK. My speeds and feeds populated. I can always change them here if I want. Now, I go over to geometry. Fusion is smart enough to find your stock extents, right? Because I've got my 100 thou on each side. So I like that. Next thing that I need to do is say my bottom height. Well, Fusion grabbed my model top as the bottom height, which is just fine. I could also come to selection and just select that. And then I could, of course, offset it if I wanted to. Okay, my passes. Let's say my step over is 2-inch 850 thou, which is just fine. I could lower that if I wanted to. And then multiple depths. In this case, I do want multiple depths because I'm not comfortable with the face mill taking 100 thou depth of cut. So maybe I say 50 thou depth of cut. In aluminum, that will be just fine. I'm going to hit OK. And I've got a decent tool path. I can simulate that just to double check. Okay. Looks good. Next, I can do my drilling. I can drill these holes, essentially. Okay. I can hit hole recognition right here, and it actually is going to come up with all my holes. Okay. So it came up with all of these holes. It came up with these ones right here. So it's saying that, hey, yeah, you can spot drill, and counterbore the hole. Or I could, bore the hole as well. So that's kind of cool that you can do that. In this case, I'm not going to. In this case, I'm actually just going to hit drill. And I'm going to select these because I'm going to pre-drill them. I'm obviously not going to pre-drill with a face mill. So I'm going to add a spot drill. Or you could do a center drill if you wanted. Matter of fact, let's do a center drill. Okay, say that's a high-speed steel tool. I'm good with that. Grab my speeds and feeds. I'm going to say, yeah, I'm actually going to go 200 surface feet a minute. I'm going to say that a 4 thou chip load is just fine. That's going to be tool number 7. That's okay. And that doesn't look anything like a doesn't look like anything like a center drill. So you'll need to change these. For the purposes of this demonstration, I'm just going to go to a spot drill. And that looks fine. It's a 2-flute spot drill, and voila. Now, I've got my geometry already selected. The heights, okay? I'm going to say the whole top is my bottom height. And I want to go down, I don't know, and this is something you got to play with, 0.1, okay? So when I look at this, it gives me a good representation of how deep it's going to go. And that's perfectly fine for a spot drill. If I wanted to incorporate a chamfer into that, I would need to go a little bit deeper. I personally don't like doing that, especially with CNC when I can follow it up with a chamfer tool, which we'll do. But just to show you, we simulate this. And that looks pretty good. Next, I would need to follow it up. And I could actually just hit this. I can duplicate it. And then I can change the geometry here. So I could actually go there, there. Remember when I was saying that it's not always the best thing to have modeled threads? Well, this is certainly a case of that. It's easier just to select the non-modeled thread. Okay, in this case, I know that that was, I believe that was a 1/4-20, so I need a 201 drill. If you didn't know, you could look on your drill chart. So I got my drill, diameter is 0.201, or number 7, that's a 2-fluter. Speeds and feeds, I'm going to drop that down to 100 surface feet. And I'm going to go 4th thou chip load. That'll be tool 8. Now the height, I'm going to say that's going to be the whole bottom. Okay. Now it's going to drill the whole bottom, and if I want to have a drill, well, actually, need to offset that. So now it's perfectly on the whole bottom. If I were to break through, I could, and I could, you know, as that diagram says, I can hit that, and it would break through the hole instead of stopping at the apex of the tool. Okay, over on the cycle, this is where I have a ton of different options. I can drill, I can do a chip breaking, which would, you know, go down and then stop, partially retract and then go down. I can do a deep drilling cycle, which will fully retract out of the hole. That'll allow those chips to come out, coolant to get back in the hole, and then you won't have your drill binding up. But there's a lot of different things in here. If I was going to tap this, which I am later, I can choose tapping. Okay. In this case, I'm good with drilling and rapiding out. It's not deep enough for me to need the peg. Oh, one thing. I can see an issue here. It's starting at that depth. I actually need to start it at the model top, because we only spot drilled, okay, and we haven't made this counterbore yet. So let's simulate that. Let's start with our drills. So it's going to spot drill. That looks great. Change tool. That's going to drill. That also looks good. Okay, voila. All right, looks pretty good. Now, instead of redoing everything, I can just duplicate that. And then I edit it. And all I'm going to do is change the tool. And I'm going to change that tool to a 1/4-20 tap. So it's a right-hand tap. 2 flutes. The diameter is 0.250. The thread pitch, don't confuse yourselves with this. It's a quarter 20, meaning it's 20 threads per inch. So it's easy. All I do is do 1 divided by 20. And voila. Fusion automatically does the math for me. And that's the great thing about Fusion. If you ever just want to do simple math calculations, you can do them straight from this dialog box. Feeds and speeds, taps. Man, I'm always below 70 surface feet a minute. In this case, I'll be about 40 surface feet a minute. 611 RPM, that's fine. I'm 9 on my tool, or whatever you deem it to be. And call that good, okay? It's going to tap to the bottom of my hole. In this case, I don't ever like that, so I'm going to have it come up 50 thou above that. And you may want to do more depending on what type of tap you're using, whether it's a bottoming tap or otherwise. I can set a dwell period in here, and I believe this is in okay, it is in seconds. Okay, so I could put a dwell period of 1 second. What that would do is it would tap and then stop at the bottom of my hole. It would dwell for 1 second, and then it would reverse. If you've got a machine that's not capable of tapping that fast, you may want to do that. That's just easier on the machine's spindle. Okay, so we'll simulate that. Again, I can just click the one I want to view. So it taps it. Looks good. It's not going to actually show the helical threads, but I know that that works. Okay. The last thing to do is to do this counterboard hole, and there's a couple ways of doing that. Being that I've already drilled it, I've made a pre-drill, I'm fine with just using a contour, and maybe I use like a 3/16 and mill. Change that to 1/875. Call that 3 fluter. Carbide, my feeds and speeds. I'll change that to 1,000. I don't have that much RPM. It's saying 20,000 RPM, so I'm going to have to go half that at least. And on the Haas, sometimes it's easier just to set the spindle speed at its max. Like on the Haas, it's saying 368 surface feet. And in this case, I'm okay with doing a 1 thou feet per tooth chip load. Again, consult your feeds and speeds worksheet, and that'll tell you what speed and feeds you can get away with. I believe I'm up to tool 10. And again, these numbers right here will change based off what machine you're working on and what tool numbers you want to set. For me, it's easier just to work up. And I always set this just so I don't forget. So I set that when I set my feeds and speeds and I create my cutter. Everything looks good. It populated correctly. Now, I want to select these. My bottom height is a selected contour. That is just fine. And in this case, I do want to have a couple roughing passes, and I want the maximum step over to be probably on that small of a cutter. Let's go 30 thousandths of an inch. And we will probably have maybe 3 or 4 of them. On the linking, I have a pre-drill position. Okay, I can choose that my pre-drilled position was there, right in the center. And I can choose that for each one. That way, it will plunge straight through the center of my pre-existing drilled hole, and that way I don't have to ramp or do anything crazy. It's giving me an error, and it's saying, cannot use drill positions because keep tool down is not activated. Okay, so I may only be able to get away with using one, I believe. So I'm going to deselect that and hit that. No. Okay, the other issue is that I've got too many step overs. So it's actually going to, let's try 2 step overs, and that fixed the issue. And you can see that I don't really like where that's coming down, so I'm going to add back in my pre-drill positions. Okay, so now we can simulate that and see how it works. Click on my contour. Slow that down a little bit. Now, if you want your tool holder to be out of the way, that's pretty easy. You just come here and do shaft, and that will only show the tool. Good, so it's not plunging into any stock. It's cleaning everything up. And that looks great. Okay, the only other thing left to do is I really like having chamfers on everything. I don't like to chamfer anything outside of the machine. And so Fusion's got a really cool feature to do that, and it's called 2D chamfer. Now, you don't want to have the chamfer modeled. You just want to have a nice sharp line like this. And so I'm going to go ahead and I'm going to create a chamfer tool. And on the Akuma, at least, because I just did it, I know we've got a 10 millimeter tool. It's at 45 degrees and the tip diameter is like 5 thou. So I think it's a 4-fluter carbide, feeds and speeds. I can run this one pretty fast. I'll run it at its max 7500, and I'm good with about 1 thou per chip load per tooth. Call it 11, hit OK, and then I select my geometry. I want these 4 tools. On the heights, it's just selected contour. And here in the passes is where you choose the actual chamfer width. So yeah, I want to have a 20 thou chamfer and my chamfer tip offset. This is how far below the stock or material that you're cutting the tip of your chamfer tool is. So remember, if you've got a 45-degree tool, the further down it is, the bigger the diameter you're cutting, and so the more surface speed has to play into it. So if you're limited on RPM, by dropping that tool, your surface speed goes up and you can go faster. In this case, 40 thou is okay. I could probably bump that up to 60 thou. There's a good diagram of the chamfer tip offset. The chamfer clearance, this is how much clearance you have between, say, another feature of a part and your tool. So in this case, it can go 1 millimeter away from another feature. In this case, I don't have anything to worry about because there's no risk of a crash. Okay, that looks pretty good. I'm going to simulate that just to double check everything. That's looking pretty good. Okay, guys, that's the basics of doing holes. Let's see, we've gone over tapping, we've gone over contours, roughing strategies, setting tooling, speeds and feeds, planes, etc. So that's a very basic CAM intro. That's enough that you can do 99% of what you'll need to do in this class if you learn those basics. So make sure to practice them. Come get me or Jeff or someone who's familiar with Fusion 360 if you have any questions. But otherwise, it's just a matter of playing with this. And the great thing about Fusion is that you can download it at home, you can use it and log into it from the school, or you can use it and log into it from your home PC or laptop. And all your files will be there because it's cloud based. So very, very cool software. Again, one thing I don't think I've mentioned in this whole video series, which is something I use quite a bit, is if I want to figure out a size of something, I can come up here to this measure, this inspect little ruler, and I can measure something. So that's telling me the diameter is 375 thou, or if I want to measure the length of something, I can click two planes, and it will tell me that as well. So feel free to utilize that quite a bit. Up here, you can also utilize different positions. So you can look at isometric views or front views or top views or whatever. That's going to conclude our 3-part video series. We've gone over the basics of navigating Fusion 360. We've gone over more intermediate skills such as on the CAD side, such as sweeps and revolves and assemblies. And then a 3rd-part series, we've of course gone over the CAM side of things. Now, it's important that when you're posting things out on the CAM side of things, you double, triple check everything. Running through things in simulation is great, but where people are going to potentially have crashes or break tools is not setting the correct speeds and feeds. The CAM simulation is pretty good at telling you what's going to happen if you set everything up correctly out on the machine and if you set your speeds and feeds correctly to begin with. So utilize our speeds and feeds sheet. Make sure that you're setting correct work coordinate systems and tool offsets out on the machine, and then triple check your setups out on the machine. And if you can, please do a dry run before you run anything. That's running things at least 3 inches above your part. All right, guys, that's it. Let me know if you have any more questions. Thanks.